I would like to start just by imagine this nice picture. I don't know if you sometimes see this nice food is named Coco Locos. Imagine the following: two main ingredients when you put inside a coconut, ice cream and fruit, and then you combine them. At the end, you get something very solid, right? So I would like to do something similar, combining dark energy and dark matter, and by conformal and deformal transformation. I don't know if it stays good or not. let me see if you want to try this kind of combination. Okay, so in doing so, I would like first to okay. I would like first to do this question. So what is the most general relation between gravity and matter? So we know that according to general relativity, both experience the same metric, right? But Bekenstein in 1993, so he formulated this nice equation, the fundamental equation, and he found the most general way to relate both sectors, the geometrical sector, the gravitational sector, and the matter sector. Okay, sometimes it's called the physical frame. So in this kind of transformation, we have here the conformal part, and this is a purely formal part of this nice transformation. Okay, so but this is nothing but the different representation of the same theory. So it means that if you want to describe some physical observable, so at the end you can do it just by this metric or by this tilde down metric. So at the end you get the same results. So in the Jordan frame, you usually have some field that couple non-minimally to gravity. So there appears some curvature there. And matter in that case involve only one experience the metric, this kind of metric, and is minimally coupled to gravity. In the Einstein frame, however, you have the opposite. So you have in the gravitational part, you have the Einstein-Hilbert 4, but the matter sector is affected by the fields. Okay, so in this way, so you have an extra terms that can mediate some kind of force, right? So it had been explored, this kind of deformal transformation in the context of scalar field. It had been used also to build scalar tensor theories, like and also looking some correspondence between scalar theories and Hordensky theory, because for instance you can apply this transformation and obtain some class of Hordensky theory. But in the case of vector field, it has been hardly treated. So the idea is just to explore what's happening when you apply a similar transformation in the context of vector tensor theories. So we do something in that direction in this paper in collaboration with Jason Rodriguez. So we imagine that the gravitational sector is described by some multi-fields in this case, and then we couple it the matter sector with this function, which also you can see the matter sector experience a different metric, and then we try to describe the acceleration expansion and the current acceleration expansion of the universe. And so in another paper, also in collaboration with Jason Rodriguez and Juan Pablo Beltran, we imagine the following. So we have here this gravitational part of the theory. So we have some scalar field coupled minimally to gravity, and also the matter sector experience the same method. But in this case, we have a difference, or we have an additional sector, which in this case experience a different metric. So in that case, we found that the vector field of this part can behave like radiation in the early universe, or even can behave like a matter, depending on some function here defined. So now I am interested in working on that topic. So I imagine the following. So it is more phenomenological. It's not, building the theory from scratch. Just this is a phenomenological position. So we have here just some Lagrangian describing the gravitational part of my theory, which depend on this X, which is a master, and this Y, which is just the kinetic theory of this Lagrangian, which is minimally coupled to gravity. But I imagine that the matter sector, my theory, speed on a different metric, G bar. So that metric is related to that and bar metric in this way, which is just a vector deformal transformation. You can see, which depend only on the vector field, and it doesn't contain information on the derivative of the vector field. And then you can also compute the inverse metric, and of course you have to take care about this function, and also you have to respect the causal structure of the space-time with this metric. Okay, so we define the energy momentum tensor for each fluid. We can see for the vector field, for matter, and for the rest of the fluids, which in principle are uncoupled, mean the radiation baryons and neutrinos. And the energy momentum tensor for matter depend, of course, on which metric you are defining your tensor. But you can relate both tensor just by doing this, by finding, the Jacobian of this transformation, and with that you can obtain what is the general form of your tensor, or your energy momentum tensor. We can do the same and trying to obtain the equation of motion for the vector field, which looks like this. But in this case, it's a very general Lagrangian. So in that case, we can see that it's sourcing by some term here, some Q alpha. So this Q alpha depend, of course, can depend on the vector field of the derivative of the vector field, depending, of course, on the deformal transformation. So in our case, that depend on the vector fields. So in this process, you can see that the continuity equation looks like this way. So there is no local conservation of each fluid, but you can guarantee the global conservation of the global conservation of your equation, your continuity equation. In the scalar case, usually you have this term, just one term, but in this vector case, you have another term which look more difficult, more involved compared to the scalar case. Let me now assume a very concrete model, a toy model, just to see how this works. So you can start just by the standard Procas theory with some potential. You found the equation of motion, and you have this, which is the source charge that by when you couple the matter and vector fields, right? Now, assuming a Friedman-Robertson working metric, and assuming just a very simple configuration for the vector field, as this temporal ansatz, just to rely the isotropic expansion, you can get your field equation in this way. In the generalized Procas theory, for instance, you have just one branch for this solution. From the vector field, from the equation of motion of the vector field, you have just one branch, A equals to 0. When you couple, you can see that now appear this there. So you can also apply this kind of transformation to a generalized Procas theory, for instance, and you have for sure another branches of the solution of these vector fields. So this is just a toy model. Indeed, you can define the equation of states in this way. You get your continuity equation. You define, as usual, pressure, energy density, and pressure. And this Q term can be written in this compact way with this gamma function, received contribution from both this conformal the conformal function, and the deformal function. So I can do that. Okay, now to see what's happened in the cosmological contest. So I started it just by dynamical system analysis. So this is the easiest way to see what's happened, to see the stability of some emergent solution. So we assume this simple form, exponential form for this potential. We define these dimensions as quantities that satisfy this Friedman constraint. And then we write this autonomous system, and we find, depending on the conformal and deformal function, many critical points. Just let me show you something, because this is just a work in progress. So I start just by studying this. I imagine this, I assume this model, which is a power law with some Q. And then your gamma, this gamma, which is very important here. Let's take this simple form. So it's constant. That depends on the power law. But if you define this exponential form, you have this quantity alpha, but also this v, which is v defined in this way. So you have that this gamma depends on some power of this v, which is the vector field. Okay, when I compute the critical point, so I get so many critical points, the standard radiation, matter point, or also matter with some contribution of the vector fields, and also this nice critical point, which is for the model 1. When you see Q, it's just a model 1, and in principle, it can drive the accelerated expansion just for if this Q take these values. Also, you have for the second model, when appear alpha, you have these critical points. So you have this contribution of the vector field here, and then you can also drive the acceleration expansion. And in the coupled case, you have also a critical point, which look very similar to the de Sitter solution, just when b is equal to 0. You have just the solution of the cosmological contest.
You have
constant Sora. Okay, so I did the same for the deformal case. So I take this conformal function equal to 1, and the deformal function. Now take this 4 with this. You have this gamma now, which you can see that is now more involved compared to the conformal case, and also depend on the value of this power beta. I took two different values of beta and found the critical point. For beta equal to 0, there are new critical point compared to this case. But when you take beta equal to -1, you obtain the uncoupled case, and when you take beta equal to -2, which is this case, you obtain new critical points in addition to this point. Okay, so you can see here that also you can drive the accelerated expansion, the current accelerated expansion, depending on the value of this lambda and beta 0 on v0, and you have also this another critical points. So the lesson here is that when you have this formal function, so you have a new emergent critical points. Okay, so just let me show you this numerical result, which are very preliminary. So you have different value of this bit of the power, and you have also different values for this b function, b0 function, which account for the deformal part of the transformation. You can see for beta 0, you have the result. The solid line represent the uncoupled case. You have here the energy density parameter versus this log A. And for beta 0, you have this one, and then you can vary the b0. You can see different solution. When you put now beta equal to minus 1/2, this the solution now are strained. You can see that it can be lower, the matter density, and then your energy now is increased a little bit. Also, it has affected the equation, the effective equation of parameter for the vector field, which is this black line, and also the effective equation for describing all the components, right? So when you vary here, so a different lambda is that exponential of the exponential parameter or my potential. When you fix the lambda, you have to compare this solid line, right? So it means that in the early universe, you don't have a variation when you vary your lambda, of course, because lambda just impact the late time universe. But when you vary your deformal parameters, you can see now, for instance, you can compare this solid and this solid, same lambda and different lambda and different value of b0 equal to 0 and b0 equal to 12. In that case, you can see that there are some differences. And also here. So it means that when you vary the b0, you can affect all the global cosmological evolution, right? So it is very interesting because you can use different cosmological data, different redshift, and try to constrain the value of this parameter. Okay, so this is my last slide, some conclusion. So we have proposed a new recipe. So with two ingredients, vector fields and dark matter, and then you couple both sector in a conformal or deformal way, just doing this deformal transformation. In that case, we see that many critical points arise in comparison to the uncoupled case, leading to interesting solution, a stable solution, a stable attractor solution driving the acceleration expansion, and also a scaling solution. So that's good. So it will be very nice just to put some observational data, just with the aim to constrain the model parameters, right? So as a perspective of this work, it will be nice to perform some deformal transformation, but also involving a special vector field, not just the temporal answer, which is very, very trivial. And you can assume, for instance, multi-fields or Nobelian vector field in your deformal transformation and try to do the same. Okay, for instance, you can also put in the dependence of the conformal and deformal function the field strength. So in that way, you can do explicit the structure of your group. Okay, it will be very nice also to do that. And finally, so just I would like also to consider the background dynamic that with study just by studying the structure formation, for instance, just computing the spherical collapse, number counts, the growth rate, and many quantities that can give us information about that conformal and deformal function. So that's all. Thank you very much. I hope you can try my Coco universe with dark matter, dark energy, all tablet. Maybe it stays good. I don't know. I hope you try